The High-Luminosity Large Hadron Collider is CERN's plan to turn the LHC from a discovery machine into a precision factory for the 2030s and beyond, without changing the collider's headline energy, but by radically increasing the rate of usable collisions. In accelerator language, it's about luminosity, how many proton-proton interactions can be delivered to the experiments over time. The February 2026 CERN press release frames High-Luminosity LHC as a generational step, a major upgrade set to enter operation in 2030, and designed to increase luminosity by a factor of 10, translating into vastly larger physics datasets and a much sharper microscope for rare processes. In Mark Thompson's words, the Director General doesn't just sell it as more data. He points to the deeper payoff, pairing upgraded detectors with advanced new data tools to reach measurements that are essentially out of reach today, including, for the first time in a realistic way at a Hadron Collider, a handle on how the Higgs boson interacts with itself, which feeds directly into our understanding of the Higgs potential and the early universe. And he underlines the honest scientific appeal. High-luminosity LHC is also about opening doors to the unexpected. If new phenomena exist at accessible scales but are rare or subtle, you only see them once you have enough well-understood collisions. That's the successor logic. The LHC's big triumphs, like the Higgs discovery, were enabled by a threshold crossing in energy and dataset size. High-luminosity LHC is the next threshold crossing in statistical reach, turning today's maybe someday measurements into routine, systematics-dominated precision physics. What makes this upgrade feel real, rather than a glossy roadmap, is that CERN is now stress testing the future machine as an integrated system, not just as isolated components. The press release's headline milestone is the start of cryogenic cooldown of a 95-meter-long full-scale test stand, a surface-level replica of the underground configuration that will sit near the ATLAS and CMS interaction regions. Bringing that long string of hardware down to 1.9 Kelvin, minus 271.3 degrees Celsius, is not a symbolic gesture. It is the operational regime where superconducting accelerator magnets live or die, and where small integration mistakes become expensive lessons. The test stand, the inner triplet string, or IT string, exists because high-luminosity LHC is not a single new magnet or a single new cavity. It is a tightly coupled ecosystem of magnets, cryogenics, powering, protection, alignment, and controls that must behave as one machine under extreme conditions. CERN's Oliver Bruning, Director for Accelerators and Technology, spells out the project logic. Individual systems have already been tested, but the goal here is to validate their integration and collective performance under real operating conditions, and to use the exercise to optimize procedures before everything gets installed in the tunnel. That wording matters. High-luminosity LHC success is not only whether a magnet reaches field on a test bench, but whether the whole region can be installed, interconnected, commissioned, protected, and repaired with realistic turnaround times once it's embedded in the LHC's operational heartbeat. The IT string is basically a rehearsal where the stage is as close as possible to the real one, so you learn the hard lessons now in an accessible hall, rather than later in a radiation-activated tunnel with a global physics program waiting on your schedule. Under the hood, High-Luminosity LHC is also a technology story, one where the upgrade forces accelerator engineering into regimes that haven't been used in proton colliders before. The press release highlights 3 examples explicitly: superconducting crab cavities that tilt bunches before collision to recover luminosity lost to crossing angles, crystal collimators designed to steer or remove errant particles more efficiently, and high-temperature superconducting electrical transfer lines to power the new magnets with minimal losses. The headline hardware, though, is the new final focus magnet system, the inner triplet quadrupoles close to the experiments, whose job is to squeeze the beams to tiny spots at the collision points. These magnets move beyond the LHC's niobium titanium technology into niobium tin Nb₃Sn, enabling substantially higher magnetic fields. CERN's own reporting on the IT string details the scale of the jump. The new Nb₃Sn inner triplets can generate fields up to 11.3 Tesla, compared with 8.3 Tesla for the current NbTi inner triplets, exactly the kind of increment that translates into tighter focusing and higher luminosity. The IT string, as assembled, isn't just one magnet. It is equipped with 6 niobium tin quadrupole magnets grouped in multiple cryostats, plus corrector magnets and a dipole that helps bring beams onto a common trajectory at the experiments, so the test stand exercises realistic magnet circuits and interfaces rather than a single device in isolation. And powering all of this pushes into new territory. CERN describes an innovative cold powering system with a long transmission line designed to carry current across a wide temperature range, including a roughly 75-meter superconducting link using novel materials such as magnesium diboride, able to transport up to 120 kiloamperes from room temperature power converters in new technical galleries down to magnets operating at 1.9 kelvins, with almost no energy loss. This is where the upgrade stops being just physics and becomes a systems engineering milestone. Magnets, cryogenics, electrical distribution, civil engineering galleries, protection logic, and installation choreography all have to work together, or the luminosity promise remains theoretical. All that new hardware is in service of one brutal reality. High-luminosity LHC will produce collisions in an environment that is dramatically more crowded and more data-intense than anything the LHC experiments were originally built for. The CERN schedule update makes the project's next steps feel concrete in calendar terms. Run 3 is extended until July 2026. Then, Long Shutdown 3, LS3, begins later in 2026, with major work starting in September 2026. And the startup of High-Luminosity LHC, Run 4, is planned for June 2030. During LS3, ATLAS and CMS will replace large parts of their electronics and many detector components, especially trackers, because you cannot exploit higher luminosity if your detector saturates, your triggers choke, or your reconstruction collapses under pileup. ATLAS's own outlook for high-luminosity LHC quantifies the experimental challenge. Leveled instantaneous luminosities up to 7.5 times 10 to the power of 34 centimeters squared per second, with up to approximately 200 simultaneous inelastic collisions per bunch crossing, pileup, and an integrated dataset of 3,000 femtobarns to the -1st, delivered by around 2041, including what was already collected in runs 1 to 3. That pileup isn't just more of the same. It changes how you build and operate detectors, timing layers to separate vertices in time, higher granularity trackers and calorimeters to reduce confusion, faster and smarter triggers to keep the interesting events, and reconstruction algorithms that can scale to the combinatorics. This is exactly why CERN is already talking about advanced new data tools in the same breath as accelerator hardware. One recent CERN physics story highlights CMS demonstrating a machine learning-based particle flow approach that can reconstruct collisions more quickly and, in some regimes, more precisely than the traditional handcrafted reconstruction chain. And notes that while it was benchmarked under current LHC conditions, it is predicted to be even more useful for the high-luminosity LHC era, where the upgrade will deliver approximately 5 times more collisions and stress every part of the analysis pipeline. In other words, high-luminosity LHC is as much a computing and inference upgrade as it is an accelerator upgrade, because the ability to turn collisions into knowledge becomes the limiting factor once collisions become abundant.
So what does high-luminosity LHC mean, beyond the engineering triumph? It means the LHC program evolves from "we found the Higgs" to "we interrogate the Higgs," and from "we search broadly" to "we measure precisely enough that tiny deviations can betray new physics." The press release leans into this idea through Thompson's framing. HL-LHC plus upgraded detectors plus modern data techniques is how you access Higgs self-interaction, a measurement that is deeply tied to the shape of the Higgs potential and thus to cosmic history. ATLAS's projections flesh out why luminosity is the currency here. With 3,000 femtobarns to the minus first power, rare channels become measurable, and even di-Higgs production, tiny compared to single Higgs, moves into the realm of observation sensitivity, enabling constraints on the Higgs self-coupling at the order tens of % level in combined analyses. It also means a new industrial and international collaboration footprint. CERN states the project is led by CERN, with an international collaboration of almost 50 institutes in more than 20 countries, with additional contributions from a wide range of member and non-member states, illustrating that HL-LHC is not a CERN upgrade in isolation, but a globally distributed R&D and fabrication effort. And maybe most importantly for how you tell the story, HL-LHC is a bet on the scientific method itself. If nature is hiding rare processes, subtle symmetry breakings, or weakly coupled new sectors, the way you flesh them out is relentless statistics, exquisite calibration, and the humility to let the data surprise you. The IT string cooldown, 95 meters of future accelerator brought to 1.9 Kelvin to prove that an integrated machine can behave as designed, is a perfect symbol of that bet. It's not just about building stronger magnets, it's about building confidence that when June 2030 arrives and the first HL-LHC beams circulate, the entire stack, from cryogenics to reconstruction, will be ready to convert an avalanche of collisions into the next decade's discoveries.